Hello everyone, in this video I'm going to be talking about the difference between the kinetic and thermodynamics control of the reactions, and they are really important, especially when you're trying to do those 1, 2 and 1, 4 addition of the reaction. So I'm not really going to talk about every single example that falls into the kinetic and thermodynamic categories, but I'll talk about the addition of hydrohalogenation, which is going to be either HCl or HBr, to the conjugated dienes, and I'll briefly talk about the Br2 as well. So you don't really have to have only the HBr or HCl. I can have the same effect if I'm adding the Br2 or Cl2, so that tags along with them as well. And these 1, 2, 1, 4 doesn't really stop here. You will see those again when you start talking about these aldehydes and ketones, alpha, beta, unsaturated ketones. So before we actually go into details of these addition reactions, I want to talk about what a kinetic control and what a thermodynamic control is. So kinetic control more or less depends on the rate of the reaction. So whatever comes faster will take place even if it's not the most stable product. Now, that does not necessarily mean it will always make the less stable product. Sometimes the kinetic control indeed does make the most stable product, but usually it has a tendency to make the less stable product because it just happens to occur faster. And they usually have low activation energy. That means they can take place at low temperature. And as soon as you increase the temperature, these kinetic products that you will have will be in thermal equilibrium, will be in equilibrium with the reactants or with the intermediates, and they can go back and forth. And if you are in the process of making a more stable product, which is going to be your thermodynamic products usually, then you will tend to convert all your kinetic products back to the intermediates or the starting material, and then it will eventually make your most stable product at high temperature. So that's what the thermodynamic control is, or equilibrium is, where it more or less depends on, are you able to make the most stable product? And they usually going to have high activation energy, um, and they will take place at high temperature. Now, why would they need high temperature? Because they have high activation energy, so you want to have enough energy given to the reactant so they can cross these energy activation barriers. So let's look at these two energy profile diagrams I have here. So I'm going to talk about this first one, the one on the left first. I have AB converted to either EF or CD, and they seems to be two different types of products because they have two different energies. So I clearly see the E and F are lower in the energy scale, so they are going to be more stable. And since they are more stable, I want to see what their activation energy is. And it turns out the activation energy for the formation of EF, I'm going to call this EA1, and the activation energy for the formation of this CD is going to be EA2. And I clearly say that, okay, your EA1 is less than your EA2, or another way of saying your EA2 is greater than EA1. So that means low activation energy will happen faster, will take place faster, and since this takes place faster, this is going to be the kinetic control. But then at the end of the day, when I look at the product, it is actually more stable. So there are going to be times when your product is going to be the most stable, and it is going to be because of low activation energy. So I can say E plus F in this particular case are indeed your kinetic and your thermodynamic products. They're favored by both the kinetic control because it takes place faster, low activation energy, and also favored by the thermodynamic control because they are more stable compared to the C and D. So that does happen, but oftentimes, every now and then, especially when you're doing these dienes and when you're doing these alpha beta unsaturated ketones and aldehydes, you may run into situations where your most when your fastest making product is not going to be the most stable. So let's look at this particular example on the right side, and I can go ahead and figure out what their activation energy is going to be. So this is going to be your EA1, and then I have for the CD, this is going to be the EA2. Now in this case, clearly your EA1 is actually bigger than EA2. So that means E and F is still going to be the most stable. So they are still going to be your thermodynamic products, but C and D are going to be your kinetic products because they are made faster. So what happens in this particular case? So if I'm doing this reaction at low temperature, so low temperature, I don't have enough activation energy to cross these activation energy barriers. So only activation energy they would acquire would be the EA2, and in that case, the C and D will be made. All right, and a lot of these products are actually going to be reversible. So at low temperature, as soon as the C and D is made, it's irreversible. But as soon as you start increasing the temperature, so at higher temperature, now C and D are going to be having enough energy to kind of go back and make A and B because they are in reversible phase. But now A and B also going to have enough energy to cross the activation energy EA1, and as a result, they're going to start making E and F as your product. So I can say at high temperature, I'll say C plus D will go back to make A and B, and then the A and B have enough energy to cross EA1 in that particular case. And once they have enough energy to cross EA1, the E plus F will be made as your major product. So that's going to be, in that case, your E and F are going to be the most stable product, and C and D are going to be your less stable product, but they are indeed made faster. So if you increase the temperature really, really high, I would say at a very high temperature. And at a very high temperature, all the products are going to be reversible. Then even E and F, they can go back and make the A and B. But you just have to like control the temperature where you don't exceed it too much, where it will set up an equilibrium. But you want to have temperature increased just enough so that you can get E and F made, and they don't go back to make A and B. So I'll say the kinetic will be made at the low temperature in this case. I want to say low temperature, that could be anything anywhere between like negative 80 degrees Celsius to 0 degrees Celsius. Really depends on the type of reaction you're really running. And the high temperature, we look at somewhere like room temperature to maybe like 40 degrees Celsius. Not like a super high temperature, just somewhere around 40 to 50 degrees Celsius is good enough to get your thermodynamic product. So this is the bottom line, the comparison between the kinetic and the thermodynamic control of the reactions. So let's look at a particular example how that's really going to work. And obviously, we're talking about dienes these days, and we're going to have these conjugated diene here. So the very first thing I can do here is the proton transfer. So I know this HBr, and I can go ahead and use one of these pi bonds. I'll just call a number of these carbons for my own convenience. So it's going to be 1, 2, 3, 4. And I'll use the pi bond between the carbon 1 and carbon 2 right here. And that's going to break up. And when I use this pi bond to do the proton transfer, where would that proton go? Would that proton go on carbon 1 or carbon 2? So that goes back to the Markovnikov's rule. And remember, if it goes on to the carbon 1, carbon 2 gets a positive charge. And since carbon 2 gets a positive charge, it does actually makes the most stable carbocation in this particular case because it's going to be tertiary and it's going to be allylic carbocation. So there's two things going on. Now, someone may ask or may wonder why not attacking the pi bond or using the pi bond between carbon 3 and 4 to do the proton transfer. Well, if you do that, then what's going to happen? I'm going to be making, so let's say, for example, if I go ahead and do that, use carbon 3, 4 pi bond to do the proton transfer, then your positive charge will cut onto carbon number 3. So carbon number 3 is in this carbocation right now is indeed allylic, but it's in a secondary. But in the bottom case, it's an allylic and it's in a tertiary. So obviously, tertiary carbocations are more stable than the secondary. So that's why you make this particular one. Now, once you have made this carbocation, I can have a resonance because obviously I got some allylic, I got this allylic carbocation here, so I can move this down here. So when I move this down here, I will get, let me just copy this down here. So I'll take away, I'll get a double bond right here, and I get a positive charge right here. So I got two types of intermediates there, or I can say resonances rather, and the stability of these resonances will be different at the end of the day when you make the final product. If you look at this, I'll call this 1 and I'll call this 2. If I look at 1, I had the most stable carbocation made, but then if I look at 2, I eventually will have the most stable alkene made because it's going to be a tri-substituted alkene versus the other alkene on the left side, on the left resonance structure is going to be mono-substituted. But between those two resonances, which one will actually makes the product at the end of the day really depends on the temperature. So as soon as you remove the Br from this, I'll have the Br close by because remember the pi bond grabs this proton from the HBr and the Br minus is still going to be close by here. So I'm going to go ahead and write down Br minus here. So if I say relative to, I'm just going to go ahead and copy this down here rather. So remember we said your hydrogen is going to get on carbon number 1, so that means your Br is still close by because it hasn't really moved too much yet because of relatively low temperature. When the temperature increases, it will start moving from carbon 1 to carbon 2 to carbon 3 to carbon 4, but right now it's very close by, so it's also called an proximity effect where since the Br is close by, it has the potential to go ahead and attack this carbon number 2. So that's how you get this kinetic control product because it's at low temperature, it hasn't really moved much, so you'll get this 1,2 product. So at the end of the day, let me just move this down a little bit. I'll have two possibilities. I'll have either my bromide attacking this resonance 1, and it's not chiral, so I don't really have to worry about the stereochemistry. I've drawn that over there as well. So when I attack this right here, I end up making this product here. I'm just going to draw that whole product again. And I have a BR here. So this is going to be your 1,2 addition product. That's one possibility. The second possibility was, okay, what if I go ahead and have my second resonance structure rather and having the bromide attacking that particular one. So this one will attack the carbon number 4, and then I end up making a 1,4 product. Now, 1,4 product is actually going to be more stable because it's a more substituted alkene that we have in there. But 1,2 is made faster because at low temperature, the bromide will not move uh, faster to the carbon number 4, so you will have this proximity effect taking place and the bromide will be attacking the carbon number 2 rather. This is how you're going to be doing the 1,2 versus 1,4 addition products. So how do you know when if you're going to be making the 1,2 or versus 1,4? Well, it all really depends on the temperature. So if the question says, okay, I'm doing this particular reaction at somewhere maybe like a negative 80 degrees Celsius to 0 degrees Celsius, so then I'm going to be making this 1,2 addition product. But if I'm doing this reaction, suppose at 40 degrees Celsius or higher or somewhere close around 40 degrees Celsius, then I'm going to be making 1,4 addition product in that particular case. Why that really matters, why the temperature plays an important role here, and we can look at this energy profile diagram here. So I'm starting at the reactant. So when I start at the reactant, I can clearly see that my intermediate is roughly the same. So I have to draw just a little bit on the side just because of the color, because I don't want to draw it on the top of the white line there. But your first step is more or less very similar activation energies and whatnot. What really makes a difference here is the second energy diagram there. So the second energy diagram, I can call that EA1, and I can call the other one to be EA2. So I can clearly see that EA1 is actually less than your EA2, so that makes it your kinetic product because that will take place faster. And then your EA2 is actually going to be bigger than your EA1, and that makes EA, at the end of the day, the EA2 does make the most stable product because of the alkene that's made in this particular case is more substituted. So this is going to be your thermodynamic products. So this is going to be done at low temperature. That's at low temperature, this is going to be your major product, and at high temperature, the thermodynamic product is going to be your major product. So that's how you know which one you're really going to be making at a particular time. Sometimes your 1,2 product is indeed going to be your kinetic and your thermodynamic product. So let me take an example here. Instead of Br2, I'll just take an HBr, just as in very similar. But you could do these reactions, have similar results when you use Cl2, Br2 as well. You can get 1,2 and 1,4 products just like we have gotten for HBr as well. In this particular case, I got this diene, so I'm going to go ahead and use this pi bond right here and grab the proton. And then in the first step, the double bond, the positive charge right here. So between those, if I call this carbon 1 and carbon 2 just for my own convenience, where would the hydrogen go? Hydrogen goes onto the carbon 1 so that you can create a positive charge on the carbon 2, because at that point, the carbon 2 is going to be secondary and it's going to be allylic. There's two things going on. But if I put the hydrogen on carbon number 2 and carbon number 1 becomes a positive charge or becomes a carbocation, then it's only tertiary, then it's not really allylic anymore. But you want to have, you have two effects there, this being positive charge on the second carbon being secondary, and allylic is going to be more stable. So once I create this, I can go ahead and do the resonance where this will move down here. And when this moves down here, I'll get this as my product here, this as my second resonance here. So now I can do two things. I can have my Br minus either attacking the first resonance, since this first resonance is actually going to be chiral, the carbon number 2, so I can have the top attack and bottom attack. So you can have two products there, or two enantiomers, pair of enantiomers rather. So I can have, take this out here, I can have the Br coming out of the page, and I can have an enantiomer of that as well. And if I use the second resonance structure, when I'm using the second resonance structure, I'm going to be attacking this particular carbon here, where that carbon is not really chiral, so I don't really have to worry about the chirality or the stereochemistry there. So I'll go ahead and get this bromine attached right here. Now, in this particular case, the next question is going to be which one is going to be your kinetic product. Obviously, your 1,2 is going to be your kinetic product because of the proximity effect, but then which one of them is going to be your thermodynamic product? And if I look at my final product, this this is the first product that I have on the left side has the double bond where I have three R groups. So this is actually going to be tri substituted alkene. But if I look at my other product, this has only two R groups and two hydrogens. So this is actually your di substituted alkene. So since this is going to be less stable, your tri-substitute product is going to be more stable. So since that's more stable, that's also going to be your thermodynamic product. So like just like I said before, kinetic products sometimes could also be the most stable, and as a result, that makes them thermodynamically controlled product as well. So that means even at high temperature, you'll still make the kinetic product, which is indeed or made fastest, and that was actually going to be the most stable product as well.